Wait, there you go. It's being recorded. So that's a beard, Will? I mean, that's what he claimed. So.
Beard in progress.
All right. Okay. Well, anyway, so sorry about that delay, but let's kind of get back to this. So in terms of linear versus non-linear, again, what it really comes down to is just the y's and the y primes and the y double primes. Okay. That's the bit that's going to tell you linear versus non-linear. All right, so what does it actually mean to be a solution to one of these? Well, I mean, you probably have a good idea of what that means. Solutions are going to be functions that satisfy the equation. So let me give you some examples of some functions, some equations, and what the solutions to these different differential equations are. So we'll go to a super easy one, something like y prime equals t. You should be able to give me a solution. Anyone want to type one in the box or throw out something over voice? What's a function whose derivative is t? Beauty, thanks, Wes. So what if we have, say, y equals t squared over 2? Right? That is a solution to that differential equation. But you guys also know that that's not the only one. Right? Thanks, Thea. Thea just said, yeah, but what about the plus c? So we throw that on there. And here's the first thing that I want you to realize is that just like before, when you solved one of these things, you get more than one possible solution. Same thing happens here. When we get differential equations that are more complicated, we're going to find there's more than one solution. And in fact, we're going to get these constants a lot. They're going to show up a lot because we're integrating. And we are already seeing that when you integrate, you get a class of functions. You get a group of functions that are all off by the scalar. So Wesley just asked, are we going to ask for the solution where you need to include the c? Always include the c. Unless you have what we call an initial value problem, and that's where you actually find the value of c, but I'll explain that in a minute. So you definitely want to get in the habit of including these c's. They are super important because really what we get at in differential equations is we're looking for the groups of functions, all of the functions that work. All right, so something like this, it's a no-brainer. You already know how to do those. But what if it was something slightly more complicated, like this guy, y double prime minus y equals 0. So first of all, it's a linear, ordinary, it's not partials, second order differential equation. Can you think of a function that would satisfy this? A function that if you differentiate it twice, subtract the original one. All right, so Trey just threw up e to the x. I like that, except I'd rather it be e to the t. We want to get in the habit of using t's instead of x's. It doesn't really matter. Like you guys know, letters are letters. But we want to allow for, usually in an applied context, we're looking at how things are changing with time. So that's why we tend to use t. All right, so beauty, I like e to the t, and Thea just threw out another one. How about cosh? Thea gets bonus points for that. All right, so you remember cosh? That's the one whose graph is the catenary, the arch, right? Its derivative is sinh. Sinch's derivative is cosh. So cosh minus cosh equals 0. So yep, there's another one. West 2 just gave me 0t. you should be really, really glad that we are social distancing, because that would have been an eraser throw, my friend. Yeah, okay, yeah. Yes, 0, of course, is a solution to this as well. You're going to see that for pretty much any equation, differential equation that equals 0, 0 is going to be a solution. We call it the trivial solution, right? But yeah, I'm watching you, man. All right, anyway, so yeah, 0t. Point is, there are a lot of solutions. There are absolutely a ton of solutions. And I don't even, not even just by putting scalar multiples, right? Like, yes, I could have 5 e to the t, 10 e to the t, negative 6 cosh. All of those are going to work. But things like e to the t and cosh are very different. They're related. I don't know how much you remember about cosh, but cosh has in it an e to the t. It also has an e to the minus t, right? So it's like some of this is in there, but it's a completely different form, and yet it's still a solution. So basically, our goal is going to be, how do we find these things? How can we start with this y double prime minus y equals 0 and get ourselves to y equals e to the t, or the cosh, or all of them, because there are an infinite number out there, right? And again, it doesn't just come to the c's. All right, so there's that guy. But you can kind of see the whole idea here is we're basically just looking for a function that when we put it in, gives us that. So I'm just curious, why cosh and not cinch, Thea? She just gave me a, I don't know.
I just thought of it as like one of the prime examples of, oh, it just flips around, but the sign doesn't change, so that the second second derivative would be itself. So
nice. Yep, no, that's a great example. And so that's one of the things that we're going to use actually when we get a differential equation and we want to find a solution, is we'll think about what kind of functions might do that, right? Like, let me give you one that's a little bit bigger and uglier. Something like, no, it's not going to be bigger and uglier. In fact, it's barely any different. I just changed it from a minus to a plus, right? So now we've got y double prime plus y equals 0. Is e to the t going to work now?
no, it's going to have to be sine instead, sine of t.
All right, so e to the t is not going to work, but Thea's right. I see Westy put that in there too. Sine would work because the derivative of sine is cosine. Its derivative is negative sine. So one example of something that would work here would be sine of t. And then Westy followed it up shortly with a cosine of t, because cosine of t would do the same thing, right? Its derivative is minus sine, that then when derived gives us minus cosine. So both of those work. I could put constants in front of them. How about I'll put a C1 and a C2, because they don't have to be the same. What about this? Could I put those two together? Would that still be a solution? What do you guys think? Yeah? No?
Yeah.
I mean, we could slug it out, right? We could find the derivatives, put them in, you know, like the derivative of this is going to be C1 cosine plus or minus C2 sine, differentiate again, plug in and work. But what if, how about we just look at it this way? If we have two functions that are a solution to a differential equation, is there some going to be? So let's just think about this. We're going to go to the same, we'll use the same one. I'm not going to name them as sine and cosine. I'm just going to say, what if we have y equals f of t is one of the solutions, and there's another one that's f of g of t. The question is, can I add these? because I'd much rather do this one time, right? You know me. You know how lazy I am. I would rather do this the one time and show that, oh yeah, then it totally works, than have to do it over and over and over.
This sort of
So what do you
reminds me
think?
of this sort of reminds me of the whole linear transformation stuff from linear. Since a derivative is a linear transformation, the sum of two parts, it'll still be the linear, the derivative of one plus the derivative of other. So wouldn't it satisfy that also?
All right. So I actually love the fact that you came up with that idea, the thought of going to linear algebra that way, because this is a linear operator.
Yeah.
Derivatives are linear operators. And you guys saw in linear algebra, and I know for some of you it might have been a while, so just smile and nod if this is one of you. But with linear operators, we know that when you have two elements that are being added and also scalar multiples, you know that those pass through, right? That when you apply a linear operator to a sum, it's the sum of the linear operator individually. And with the scalar multiple, same kind of deal. So yeah, it turns out that we know that this is going to be true for any differential equation that's linear, right? So for a linear differential equation, you can make use of that fact that you learned in linear algebra, that it is a linear operator, which allows for the scalar multiple. So it turns out that if you had any two, say for this, this one, you could take any linear combination. And that's why you're going to see us do this a lot when we're going to write out solutions. We'll use C's, obviously, because we're C's. Oh, and I just realized you may not see the board. Let me switch again real quick.
So you use the C's because they're constant, but we'll call them C1, C2, C3, all the way down to Cn, whatever it happens to be. But you can take any linear combination and it will be a solution to your differential equation. So that's kind of nice, actually. One of the things that we're going to be working on then is trying to figure out, are there a basic set of functions whose linear combinations are also all solutions to this differential equation? And I don't know, since we were talking about linear algebra, that might sound familiar as well. What do we call that? A set of things whose linear combinations, end up spanning the whole solution set? Yeah, Trey. This is basically, we are finding a space. There's a solution space, right? Every differential equation has a solution space. And what we're going to be looking for, these guys, these F and G and whatever else, they're a basis for that solution space. So now you can start seeing why we had you take linear algebra first. You didn't have to take it before taking diffeq, but even on day one here, we're starting to talk about things that are relevant to what you did in linear algebra. So one of our goals is going to be, given a differential equation, try to figure out a basis to the solution space, right? Oh, okay. Thanks, Thea. Is that why she ran away? I know she's not in here anymore. I hope it wasn't because of that. I'll make sure to fill her in. It's not necessary to know that, but it will help you that do know about spaces, how to go about that. All right, so basically what we're looking for are spaces. We're looking for solution spaces to the differential equations. All right, so questions so far, how we doing? Love and life, everything good? All right, cool. So the first set of homeworks that I give you, and I'll probably, not probably, I will post something later today on the Canvas shell. And also I apologize for the fact that that Canvas shell being so Spartan right now, but I will post something that has some homework from the first chapter at least at some point today. But what you're going to be asked to do is actually classify differential equations and see whether or not things are actually solutions. But another thing that we're going to be really interested in is finding those C's, finding out what the actual C values are. And we call these initial value problems. From henceforth, I'm going to call them IVP, initial value problem. But these you're familiar with, for sure, from physics. Do you remember what you had to have in order to figure out a C? Like back in the day? Like even go just a real basic, we're just finding the antiderivative of, you know, e to the x kind of thing. Zero vector, not really a vector.
Was it like an initial value for one of the derivatives that you
yeah,
can
so
then,
we got a couple of people chiming in here. We got bounds, an initial value, things like that. Yeah, if we knew anything about the function, it allowed us to actually figure out what that C was. Let me give you an example of one that you would have seen, okay? This would have been like from beginning physics kind of deal where let's just go to gravity, right? We've got our acceleration is equal to negative g. So then you go and you find your velocity, so you integrate that, and you get minus gt plus c. But we were able to replace that c by saying something like, all right, what if we knew that our initial velocity was, well, I'll call it v naught. And what we could actually do is plug this into this relationship to solve for the c. So in this case, we would get v naught is equal to minus g times 0 plus c, which gave us c equals v naught. All right, so that initial condition made it so that we could get rid of that c. We just had to know about the initial velocity. No, Will, the initial value doesn't always give you the C. In this case, it does, because we're just, we're plugging in 0 and it's making all that other stuff go away. But that's not always the case. And I'll show you a real quick example as soon as I'm done with this. I'll show you an example where the initial value isn't the C. I know, it's because I see on the screen it says Will and then I lose it, so. I'll try to call you Wes. Forgive me. It's one of the many sacrifices we have to make during this very difficult time. There we go. All right, so then we would take one more step, right? You got your V, you want to get your position, you'd integrate again. And that would give us another C that we could then use. So initial value problems are all about, we know something about the function that allows us to actually find that C. So let's see if we can calculate a C value knowing something about the function. So let me give you an example here. And we're going to turn it into a second order differential equation. I want to give you one that is maybe a little bit more complicated in terms of finding the solution and finding the C and all that. So let's try this one. Let's go with y double prime plus 2y prime minus 3y equals 0. And I'm going to tell you that what we know about this are a couple of things. We know that y of 0 is equal to 1, and y prime of 0 is equal to negative 1. So this is also a little bit different because now there are two pieces of information that I'm giving you. Well, that's because it's a second derivative. Just like with that, you know, gravity position thing, If you have just the initial velocity, that's not enough. If you have just the initial position, it's not enough. You need both. Kind of the same deal. You're going to see that initial value problems, you need as many pieces of information as the order of the diffie-q. All right, so if this was a third order, you'd have to have 3 things on your list of given information and so on. All right, but because I know you don't know how to solve these yet, let me give you the basis for the solution space, okay? I'm going to tell you that one of the functions that works, so we'll call it y1, is our good friend e to the t. I don't know if y'all saw that. Some of you may have noticed that e to the t is totally going to work because its derivative is itself, and so is its second derivative. So we're going to get e to the t plus 2e to the t minus 3e to the t. That's going to equal 0. So that's one you might have been able to spot just on your own, right? We'll learn later how to figure these out. It's actually not hard. It truly is monkey math. But here's the second one. Let me give you a second one that works. And this guy is e to the minus 3t. I'll let you confirm that that works. Obviously, when you differentiate, it's just going to give you e to the minus 3t, but with some scalars out front, right? Some different coefficients. But the coefficients that come from the minus 3 are such that when you put it into the diffie-q, you'll get 0. All right, so there are our solutions, or at least a basis. They are linearly independent. Clearly, one's not a multiple of the other. So they do form a basis. But let's see if we can figure out what the C's are. So in general, our solution looks like this. It's y equals C1 e to the t plus C2 e to the minus 3t. But let's see if we can figure out what those C's are. So here's where we're going to use our information that we were given. So if we start with this one, y of 0 equals 1, we know that we're going to get 1 equals C1 e to the 0 plus C2 e to the 0. So whatever C1 and C2 are, I know that they have to add up to 1. All right, well, that's what that tells me. So now let's go to the second piece. So we've got that the derivative at 0 is equal to -1. Well, let's get the derivative real fast. The derivative of this thing is C1 e to the t minus 3C2 e to the minus 3t. And now when we plug in this initial value, we get -1 is equal to C1 minus 3 C2. All right, so again, whatever C1 and C2 happen to be, they have to satisfy this guy. Well, Trey, we could use a matrix. We don't necessarily have to because this is a nice simple one. But yeah, we got a system of equations. Right? We found out that C1 and C2 have to satisfy both of those, so it's just a matter of solving this system. Real quick, I just noticed, Wes, that you put up there that 0 would work for this as well. 0 would work for the differential equation, but it's not going to work for the initial value problem, right? Because 0 doesn't equal 1 ever, and its derivative doesn't equal -1 ever. But just as a solution, sure, it would have been when C1 and C2 are both equal to 0. All right, well, we can go ahead and solve this. It's not too hard. Subtract the bottom one from the top, say. You're going to get 2 is equal to 4C2, and we end up with C2 is equal to 1/2. And then once we know that C1 is also equal to 1/2. So the solution to this initial value problem is y equals 1/2 e to the t plus 1/2 e to the minus 3t. So we basically found the one set of those that gives us this function. I'll go back to linear algebra speak for you. Remember when we talk about a basis and it spans the space, that means you can get any element in that space from it, right, as a linear combination. This is basically telling us, how do we find the specific element? The specific element is the function that goes through the point 0, 1, that has a slope of -1 at 0. So that's kind of how that plays out if you want to tie it back to linear algebra. But this is something else that you're going to need to do when you're working on your homework, is trying to find the C values, solve these initial value problems. But it really is this easy. It just tends to give you systems. All right, so watch out for that, but you know how to deal with systems. If nothing else, like Trey said, throw it in a matrix, do your good old RREF. That's supremely important when they get to be big, right? Like you can imagine, like I was telling you, that the number of pieces of information you need is always going to be equal to the degree of the, or the order of the differential equation. So imagine we have a differential equation with like a 6th derivative. That initial value problem is going to have 6 pieces of information, which is going to give you 6 equations that you need to solve. You end up with a 6 by 6 matrix. Yeah. Yes, you could just, Mikey just said you could just do REF, and that definitely works. I suggest going all the way to RREF if you're using technology, because then you can just read off your solutions at the very end. But you are correct that REF works just as well. All right, so are we feeling okay with the idea of what's going on here? I mean, I know that we haven't solved a single one yet that didn't require just either guessing or an integration technique that we already know, but are we feeling okay with the idea? Yeah, thumbs up, thumbs down. All right, looking like I'm getting mostly thumbs up, so we're feeling all right. Okay, I still don't want to talk about yet how we solve these things. That will come. But I do want to show you another thing. Let me see if I can get my screen to share it. I didn't have much luck with screen sharing earlier today. All right, my window closed. Give me 1 second here.
So I have a bit of a question.
Sure, go for it.
So like when you went from one step to the other, how is there more of a systematic way of finding individual solutions to that? Is it just doing the monkey math and just taking the derivatives and finding functions that fit the bill,
Yep,
essentially?
It's purely the monkey math.
Okay, cool.
Yes, let me get in screen so you can see me. No, it is, at that stage, you do just take a derivative, second derivative, third derivative, plug your stuff in. Unless you might get lucky and it could be a form that you can recognize a little bit easier, but in general, no, it's just monkey math. Yeah, diffie-qs is all kinds of just plug and chug. And so, you know, it is what it is. All right, I'm having trouble with my screen here. I had something up in Chrome, but Chrome shut down, and now my computer, I think my computer's angry because I'm making it do so much zooming today. Okay, well, let me remind you about something. You remember vector fields? Either from linear algebra or from calculus? What did we use those things for? All right, so Trey just threw out for curl, like it's a good way of visualizing when curl happens. Also divergence. Okay, so Westy just threw out, you're plotting the derivative at a point, and that is exactly what you did. So like with vector fields, let's go back, I'm gonna make it in terms of X. But like, let's say we had Y prime is equal to, say, X plus Y. And what you did when you had a vector field is you basically went, all right, if I'm at these various points, what's the slope? And you would draw a vector, right? So like if we were at the origin, let's say, you have 0 plus 0, you know that your derivative is equal to 0. Hold on a second. I'm jumping ahead. This was vector fields, right? So you'd put 0 and 0, you plug it in, you get 0 as your vector. Let's do it this way. All right, so like at 0, 0, you get 0 plus 0, it's a vector of 0, so there's no arrow. If you went out, say, to 1, 1, at 1, 1, you would get 2, 0, so we would draw the vector that was length 2 pointing out in that direction. And you basically just follow this process for any point. Like if we came down here to 0 minus 1, that's going to give us minus 1, 1. So that would be a vector that points that direction and so on. So you kind of remember that a little bit, I hope. And the whole point of these was to have a visual representation of the field so that you could do things like divergence and curl and all that good stuff. Okay, well, we're going to do pretty much the same thing when it comes to differential equations, except we're going to call these things slope fields. Because we're not making vectors anymore. We're just looking at slopes. And what I first started writing out when I was doing this as an example was the example of a slope field. So here is a differential equation. So real quick, with either your fingers or in the chat box, what's the order of this thing?
1.
All right, so it's order 1. Good. It's a first order because it's just the first derivative. Linear or not linear? Thumbs up linear, thumbs down none. Thumbs up, good, it's linear. So it's linear, first order, ordinary differential equation. All right, now, we don't know what the solutions are to this, right? Some sort of function whose derivative is that function plus x. I don't know, you might be able to think of one. Can anybody think of a function whose derivative is equal to the original function plus x? I love seeing the faces and the looks of what's going on. Oh, so Wes just gave me 0. 0 work? This is when him being a smartass didn't pay. Y equals 0. Y equals 0 is not a solution. What's the derivative of 0? It's also 0. 0, does that equal x plus 0? No. Right? So, all right, well, point is, we don't know what the solution is, but we can get an idea of what the solutions would look like, especially if we have an initial value problem. So here's what we're going to do. We're going to draw a slope field, which is the same idea as before, where we're going to go to various points. But what we're going to do is we're going to plug in those points and figure out what the slope would be at that location. So let's say we're at 1, 1, right? At 1, 1, we would get a slope of 2. So I'm going to try to make this look like it's got a slope of 2. if I was at 1, 0, I would get a slope of 1. So it's going to be flatter. At 1, -1, I would get a slope of 0. At 1, -2, I'd get a slope of -1, and so on. So you notice what's happening is these things are doing that. And then I could do that for other values as well. So like 0, 1, I get a slope of 1. 1 - 1, I get a slope of 0. Okay, so basically I just kind of keep doing this. There's going to be another one that's out here. And let me show you how this would help us in terms of finding the actual solution. So let me say we had an initial value problem that what we knew is that at the original y of 0 was equal to 1. So think about what that just told me. That told me that it goes through the point 0, 1. So my function actually needs to go through this point right there. But I need a graph such that it's tangent at that point. Well, if I start moving in this direction and be tangent, notice it has to flatten out. And then it has to curve up and curve up more and the same kind of thing. What's that kind of looking like? Now, can you make a guess on what kind of function it would be? Maybe some sort of like West 2 in there, a parabola, maybe a quadratic. Like think about it. If you differentiate a quadratic, let's just go to a generic quadratic here real quick. So we've got y equals ax squared plus bx plus c. And we differentiate. We get 2ax plus b. All right. So let's just think about that. Would this work for this differential equation? Is its derivative equal to its original function plus x? Well, think about adding x to this, to y, right? If I add x to this line right here, do I get the second line? You should all be shaking your heads. Absolutely not, right? Because this is a quadratic. If I add an x, I don't get a linear function. Okay, so even though it started looking like a quadratic, the problem is this isn't actually a quadratic. It's a function that looks like that. It looks like a bowl, but you know lots of functions that look like bowls that are not quadratics, even ones that are not polynomials. Let's go back to earlier when Thea threw out cosh for that other example, right? So we do have to kind of be careful with these slope fields. But if we've got a slope field, we can actually use it to help us draw a graph of these functions. All right, so I just actually looked back on my Chrome, and I think I got it. So I'm going to go ahead and share this window with you guys, show you an example of a slope field. I'm trying, I promise. All right, I think we got it. All right, so can you all see it? Yep, I see some thumbs up. All right, awesome. All right, so this is just from good old Encyclopedia Britannica, no big deal. But you'll notice that this is a slope field. If you look really closely, you'll see there's these blue dashes. those are the little tangent lines. Those are the slopes at those specific points. Okay, so like if you look at where the tip of my arrow is right now, if you were to plug that X and Y, oh, and I cannot believe it. Take a look up in the corner here. See what the differential equation is? Y prime equals X plus Y. That was exactly the one I was just showing you. Boy, did I get lucky. Okay, anyway, but you can kind of see that sort of parabola nature, right? But it's not really a parabola. It sort of flattens out. And we just didn't see that because we didn't go far enough. But each of these little blue lines is showing us the derivative at any one point. Now, you'll also notice that there are some green lines on here. Well, those green lines are solutions to this differential equation at different initial values. Like this first one, the one I'm on here, the green that goes through the origin, that's the one where the initial value would be y of 0 equals 0. And if you follow the slope lines, it would actually create that green curve. This green one, I don't know where its initial value is, this other guy down here, but notice it has a completely different shape. And it's got a completely different shape because of the fact that it started at a different place. But you can follow those blue lines to help you get an idea of what the shapes actually would be. So just take these for what they are. They're really just another way to visualize and get solutions even if you don't know what the actual solutions are. All right. Anyway, so again, so far so good. All right, I think I'm going to stop here just because, to be honest, I've been talking for 3.5 hours and I need a half-hour break before I talk with Ian a little bit more about physics. But like I said, I will get you guys some homework stuff put up, well, by tomorrow. I want to be real with you guys.
I lost your sound.
Yeah, because I muted myself.
There you go.
But since I'm going to have a couple hours of class after this, I'm not going to be able to get to it right away. So, but for sure by tomorrow, I'll have homeworks up for the first few chapters. So don't worry about what sections are due just yet, but we are going to start with section 1.2. There is no homework from 1.1. 1.1 is really just, here's what's going on. Anyway, so anyway, it's good to see everybody. Like always, let me know if you have great ideas of what we can do to make this better. I'm all about improving it, and I don't necessarily know the best, right? So we'll work this out together. It's going to be a crazy quarter, but it'll be a good quarter. It's just not what we're used to, but we'll make it work. All right. So I'm going to go ahead and sign off, stop recording this thing, and it was good seeing you, and look forward to seeing you guys on Wednesday, if not before.
Sounds good.